Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. Today we will discuss Pumparounds and tower heat flows. There are two ways to remove heat from a distillation tower: top reflux and circulating reflux. In this video, we call a circulating reflux stream a pumparound. The vast majority of fractionators have top reflux. Cold liquid from the reflux drum is pumped onto the top tray of the tower. The cold liquid flashes to a hotter vapor. For example, let's say 1,500 pound/hour of liquid butane at 100 degrees Fahrenheit flashes to 1,500 pound/hour of vapor at 260 degrees Fahrenheit. The specific heat of butane is 0.6 BTU per pound degree F. The latent heat of butane is 130 BTU per pound. Latent heat means the heat needed to change a pound of liquid into a pound of vapor at the same temperature. The heat removed by the top reflux is 260 degrees Fahrenheit minus 100 degrees Fahrenheit times 0.6 times 1500 equals 144,000 BTU per hour equals sensible heat. Plus 130 times 1500 equals 195,000 BTU per hour latent heat divided by 339,000 BTU per hour equals total heat removed. Pumparound heat removal. This picture shows an alternate method, called circulating reflux or pumparound, to remove heat from a tower. Hot liquid at 500 degrees Fahrenheit is drawn from tray 10, which is called the pumparound draw tray. The liquid pumparound is cooled to 400 degrees Fahrenheit. The cooled liquid is returned to the tower at a higher elevation onto tray 9. It appears from picture that the cold 400 degrees Fahrenheit pumparound return liquid is entering the down comer from tray 8. This is often good design practice. Tray 9 is called the pumparound return tray. The purpose of the pumparound is to cool and partially condense the upflowing vapors. The vapors to pumparound tray 10 are at 600 degrees Fahrenheit. The vapors from the pumparound return tray 9 are at 450 degrees Fahrenheit. There are two pumparound trays, 9 and 10, in the column. This is the minimum number used. A typical number of pumparound trays is 2 to 5. Let's calculate the heat removed in the pumparound circuit shown in picture. Assume that the specific heat of the pumparound liquid is 0.7 BTU per pound degree F. 500 degrees Fahrenheit minus 400 degrees Fahrenheit times 0.7 times 1,000 pound/hour equals 70,000 BTU per hour. I have not shown the flow of liquid on the cold side of the pumparound heat exchanger in picture, but we can calculate its flow. Let's assume that the specific heat of the cold side liquid is 0.5 BTU per pound degree F. Then the cold side, or shell side, flow is 70,000 BTU per hour, divided by 300 degrees Fahrenheit minus 200 degrees Fahrenheit, times 0.5 BTU per pound degree F equals 1,400 pound/hour. What I have just illustrated is the most powerful tool in my bag of tricks, calculating a flow from a heat balance. What is the purpose of a pumparound? Why do we wish to remove heat from the vapor flowing up through tray 10? The circulating pumparound is cooling the vapor flowing through tray 10 from 600 to 450 degrees Fahrenheit as it leaves tray 9. But for what purpose? Picture shows the rest of the tower we have been discussing. Note that the tower top reflux flow is controlling the tower top temperature. If we were to reduce the pumparound circulation rate, less heat would be extracted from trays 9 and 10. More and hotter vapor would flow up the tower. The top reflux temperature control valve would open. The top reflux rate would go up. The vaporization of reflux on the top tray would increase. The overhead condenser duty would increase. The decrease in the heat duty of the pumparound heat exchanger would equal the increase in the heat duty of the overhead condenser. Thus, we say that the heat balance of the tower is preserved. Some of the heat that was being recovered to the cold fluid, shown in picture, is now lost to cooling water in the overhead condenser. This shows the most important function of Pumparounds, recovering heat to a process stream that would otherwise be lost to the cooling tower. Let's say that the cooling water outlet temperature from the condenser was 140 degrees Fahrenheit. This is bad. The calcium carbonates in the cooling water will begin to deposit as water hardness deposits inside the tubes. It is best to keep the cooling water outlet temperature below 125 degrees Fahrenheit to retard such deposits. Increasing the Pumparound heat removal will lower the cooling water outlet temperature. Another purpose of the Pumparound is to suppress top tray flooding. If tray 1 or 2 in picture floods, the operator would observe the following. The tower top temperature would increase. The distillate product would become increasingly contaminated with heavier components. If this were a refinery crude fractionator, we would say that the endpoint of the naphtha overhead product would increase. The pressure drop across the top few trays would increase. The liquid level in the reflux drum would increase. If the operator increases the reflux rate to reduce the tower top temperature, the top temperature will go up rather than down. This is a positive indication of top tray flooding. The correct way to suppress top tray flooding is to increase the Pumparound duty. This can be done by increasing the cold fluid flow through the Pumparound heat exchanger, or the Pumparound flow itself could be increased. Either way, the flow of vapor flowing up to tray 8 will decrease. The flow of vapor through trays 1 to 7 will also decrease. The low vapor velocity will reduce the tray pressure drop. The ability of the vapor to entrain liquid will be reduced. The height of liquid in the downcomer will be reduced, and tray flooding will be suppressed. Increasing Pumparound heat duty will unload the overhead condenser. This will cool off the reflux drum. A colder reflux drum will absorb more gas into the distillate product. Less gas will be vented from the reflux drum, and this is often desirable. Finally, it is best remembered that, as we said earlier in this chapter, heat recovered in the Pumparound heat exchanger is often a valuable way to recover process heat. Heat not recovered in the Pumparound exchanger is lost to cooling water in the overhead condenser. Do Pumparounds fractionate? The process design engineer typically assumes that a Pumparound is simply a way to extract heat from a tower. The engineer does not expect the trays used to exchange heat between the hot vapor and the cold liquid to also aid in fractionation. In practice, this is not what happens. Let's refer back to picture. Note that the vapor temperature leaving tray 9 is 450 degrees Fahrenheit. The temperature of the liquid leaving tray 10 is 500 degrees Fahrenheit. This sort of temperature difference shows that fractionation is taking place across the Pumparound trays. The temperature difference between delta T equals temperature of liquid leaving a lower tray minus temperature of vapor leaving a higher tray is a measure of the amount of fractionation. The bigger this temperature difference, the more the fractionation that is taking place across the trays. I have run plant tests that indicate that increasing Pumparound circulation rates increases this temperature difference up to a point. However, if the circulation rate is increased past this point, then the temperature difference is reduced. This idea is expressed best in picture. As the Pumparound rate is increased, tray efficiency is improved. However, at some point, the Pumparound liquid flow becomes too great. Probably, at this point the downcomers start to back up. Tray efficiency is impaired because of this downcomer flooding. The temperature difference between the liquid leaving the Pumparound draw tray minus the temperature of the vapor leaving the Pumparound return tray becomes smaller. This point is called the incipient flood point for the Pumparound trays. How top reflux affects vapor flow. Let's assume that the vapor flow into a tower is constant. Picture shows such a situation. Both the pounds per hour and temperature of the vapor flowing up to tray 9 are constant. This means that the heat flow into the tower is constant. Now, let's increase the reflux rate. Certainly, the result will be the tower top temperature will decrease. The gasoline overhead product flow will also decrease. But what will happen to the flow of the vapor leaving tray 3, 4, or 5? I ask this question assuming that the pump around heat duty is fixed. Will the pounds per hour of vapor flowing through trays 3, 4, or 5 increase? Decrease? Remain the same? The correct answer is that the weight flow of vapor will increase. Surprised? Most people are. Let me explain. When we increase the reflux rate, the tower top temperature drops, let's say from 300 to 240 degrees Fahrenheit. Actually, the temperature of the vapor leaving all the trays in the tower will decrease. The effect is bigger on the top tray and gradually gets smaller as the extra reflux flows down the tower. If the top tray temperature has dropped by 60 degrees Fahrenheit, then the vapor temperature leaving tray 9 might drop by only 5 degrees Fahrenheit. Let's assume that the extra reflux causes the temperature of the vapor from tray 4 to decrease by 40 degrees Fahrenheit. We can say that the sensible heat content of the vapor has decreased. Sensible heat is a measure of the heat content of a vapor due to its temperature. If the specific heat of the vapor is 0.5 BTU per pound degree F, then the decrease in the sensible heat content of the vapor when it cools by 40 degrees Fahrenheit is 20 BTU per pound. A small portion of this 20 BTU is picked up by the increased liquid flow leaving tray 4. The main portion of this heat is converted to latent heat. This means that some increment more of the liquid on the tray turns into a vapor. But where does this extra liquid, which vaporizes on the tray, come from? It comes from the extra top reflux. The vaporization of the extra reflux cools the tray. The extra vapor generated adds to the vapor flow from the tray. This increases the vapor flow from the tray. Even though the heat flow into the tower is constant, increasing the top reflux does increase the pounds of vapor flowing up the tower. Reflux effect on vapor molecular weight. Let's assume the following for the tower shown in picture. Constant vapor flow to tray 9. Tower top reflux flow increased. Pump around duty is constant. As a result of the increased reflux rate, the tower top temperature drops. Gasoline flow drops. This is the same problem I discussed previously. It will result in an increase in the mass flow of the vapor through trays 3, 4, and 5. But what will happen to the molecular weight of the vapor? Will it increase, decrease, or remain the same? The answer is that the vapor's molecular weight will decrease as the reflux rate is increased. But why? The vapor leaving each tray is in equilibrium with the liquid. This means that the vapor leaving each tray is at its dew point and the liquid leaving each tray is at its bubble point. As the top reflux rate is increased, all the trays are cooled. The vapors leaving trays 3, 4, and 5 are cooled. As a vapor at its dew point cools, the heavier components in the vapor condense into a liquid. The remaining vapors have a lower molecular weight because they are lighter. But this is only half the story. Let us continue. As the heavier components in the vapor condense into a liquid, they give off heat. This heat is called the latent heat of condensation. This latent heat is picked up by the liquid flowing across the tray. This liquid flow is called the internal reflux. This latent heat promotes extra vaporization of the internal reflux. Naturally, the lighter, lower boiling point components preferentially vaporize from the internal reflux. These lighter components have a relatively low molecular weight. The uncondensed vapors flowing from the tray below, plus the newly generated vapors from the reflux, flow to the tray above. The combined molecular weight of vapors is thus reduced. As the molecular weight decreases, the volume of each pound of vapor increases. As the molecular weight of the vapor decreases, the density of the vapor decreases. As the density of a vapor is reduced, each pound of vapor occupies more volume. It is true that cooler vapors do occupy less volume per pound than do warmer vapors of the same composition. That is, gases and vapors tend to contract on cooling and expand on heating. However, this is a small effect compared to the increase in the volume of vapors, due to the decrease in the vapor's molecular weight. Reflux effect on vapor volume. Now, let's summarize the effect on vapor flow due to increased reflux. Again, we are considering trays 3, 4, and 5 in picture. 1. Increasing the top reflux increases the pounds of vapor flow. 2. Increasing the top reflux increases the volume per pound of the vapor. 3. Increasing the tower top reflux rate increases the rate, in cubic feet per second, of vapor flow through the trays, because of the combined, additive effect of factors 1 and 2. How, then, does increasing the top tray reflux rate affect the vapor and liquid loading on the trays below? Obviously, the liquid flow rate increases. But so does the vapor flow rate. Does this mean that trays 3, 4, and 5 could flood because the top reflux rate was increased? Yes. Does this mean that we could flood these trays without increasing the heat flow into the tower? Yes. Does this mean that we could flood these trays without increasing the pounds of vapor flow into the tower, simply by raising the reflux rate? Absolutely correct. If an increase in the tower top reflux rate causes the top of the tower to flood, how should the operator respond? He should then increase the pump around flow to reduce the pounds of vapor flow to tray 5, as shown in picture. But suppose this causes the pump around trays 6, 7, and 8 to flood because of the extra liquid flow? He should increase the cold liquid flow through the pump around heat exchanger. If this cannot be done either, the tower pressure can be increased. This will increase the density of the flowing vapors and shrink the volume of the vapors that the trays must handle. The effect of increasing the reflux rate on a crude tower, even with a constant condenser duty, will be to increase the condenser pressure drop. This happens because the volume and the weight of the tower overhead vapors will increase as the tower top temperature drops. In one refinery, the crude tower reflux rate was increased by 25% and the tower top temperature dropped by 50 degrees Fahrenheit to 60 degrees Fahrenheit. The overhead condenser delta P increased from about 12 to 24 psi. The tower pressure was kept constant, but the reflux drum pressure declined from 17 to 5 psig. The mechanism that accounts for this is twofold. 1. Reducing the tower top temperature converts some of the heat content of the vapor to latent heat of vaporization of the top reflux. 2. The molecular weight of the vapors leaving the top of the tower is reduced. How to improve fractionation? Here is our problem. A refinery crude distillation tower is producing gasoline, truck diesel, and a gas oil. The diesel is contaminated with the gas oil. Also, the gas oil is contaminated with the lighter diesel. As shown in picture, the vapor flow into the tower is constant. Our job is to improve the degree of fractionation between the diesel and gas oil. Our objective is to remove the relatively heavy gas oil from the diesel and to remove the lighter diesel from the gas oil. We could reduce the amount of diesel product drawn from the tower. That could wash the heavier gas oil out of the diesel. But it would also increase the amount of diesel in the gas oil. Increasing the heat removed in the pump around would have a similar effect, less gas oil in diesel, but more diesel in gas oil. How about decreasing the heat removed in the pump around? This would seem to allow the lighter diesel to more easily vaporize out of the gas oil product. But will this action result in increasing the contamination of diesel with heavier gas oil? This answer is no, but why not? Reducing the pump around heat removal duty increases the vapor flow from tray 8 in the column shown in picture. The extra pounds of vapor flow up the tower and raise the tower top temperature. The reflux control valve opens to cool the tower top temperature back to its temperature set point. Then the liquid flow rates from trays 1, 2, and 3 onto tray 4 all increase. If the diesel draw-off rate is maintained constant, the liquid overflow rate onto trays 5, 6, and 7 will increase. This liquid flow is called the internal reflux. Trays 5, 6, and 7 are the trays that fractionate between diesel and gas oil. The more efficiently they work, the less the contamination of the adjacent products. The way we increase the fractionation efficiency of trays is to make the trays work harder. The correct engineering way to say this is, to improve the separation efficiency between a light and heavy product, the vapor flow rate through the trays is increased, and the internal reflux flowing across the trays is increased. Again, this improvement in the degree of fractionation developed by trays 5, 6, and 7 is a result of reducing the amount of heat duty removed by the pump around flowing across trays 8, 9, and 10. Flooding the fractionation trays. Reducing the pump around duty increases the tray loadings on trays 1 through 7. But in so doing, the trays operate closer to their incipient flood point. This is fine. The incipient flood point corresponds to the optimum tray performance. But if we cross over the incipient flood point and trays 5, 6, and 7 actually start to flood, their fractionation efficiency will be adversely affected. Then, as we decrease the pump around heat removal duty, the mutual contamination of diesel and gas oil will increase. From an operating standpoint, we can see when this flooding starts. As we decrease the pump around duty, the temperature difference between the diesel and gas oil product draws should increase. When these two temperatures start to come together, we may assume that we have exceeded the incipient flood point and that trays 5, 6, and 7 are beginning to flood. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.